Good evening and a very warm welcome from my side to this evening's lecture, which is called Niels Bohr, What He Said and Why It Matters. This evening's lecture is organized between the AJE and the Danish Cultural Semester here in Ispra. The lecture this evening will be given by David Wilkinson, that many of you may know, and who is sitting here on the right side, just waiting to take the mic from me and get into business, so to speak. But just to give a very brief introduction about David. If the JRC can be counted as a little institution within the European Commission, I think we can say that David is an institution within the JRC. David started in the JRC in '95 and has held 5 different director posts. So he has really been around and he has pushed a lot of the work of the JRC forward. That's one advantage. The second advantage is also that more or less all people in the JRC, at least until recently, have at some point in their career, they have had David as their director. And that includes myself. Now, David is not just a JRC legend, but he also holds a PhD in theoretical physics from the Cavendish Laboratory in Cambridge. And since he retired a few years ago, he has really put the word active senior into its right proportion, because David has continued to be very active for science, for cultural issues. He has continued as well with his work within the JRC. Currently, he is working on a book on the history of the Joint Research Center, which we are all looking forward to reading. Now, a bit about this seminar or lecture this evening. I called David quite a few months ago. And I said, David, you know, we are going to have the Danish Semester, and we would like to link it to science. There are a few options of famous Danish scientists, but the one I prefer the story of is definitely Niels Bohr. And then David said, I will give it a thought. And a couple of weeks after, David called back and said, yes, I have all my ideas clear now. I will do research, and then let us have a lecture on Niels Bohr. What David will bring to us this evening is, of course, the work of Niels Bohr. So his research on quantum mechanics and nuclear physics. But David will also go well beyond, because he will use Niels Bohr and show how important it is to collaborate in the field of science and what the impact of such a collaboration may have. He will also show how important it is that science takes responsibility. And this is illustrated in particular with what Niels Bohr did following the Second World War, which David will talk us through in a moment. What is a very strange paradox is that although Denmark is the nation which fostered Niels Bohr a long time ago and who had such an impact on nuclear research, nuclear energy, then Denmark has continued since the 70s to be a very anti-nuclear energy nation. In fact, I was growing up in the 70s in Denmark, and you were really socially out if you would not have a little stamp in yellow where it said nuclear energy, no thanks. But that does not take away from the fact that throughout schooling and obviously during high school and university, we were always reading and studying the works of Niels Bohr with a very high respect. I had the pleasure yesterday, together with 320 people within the JRC, to hear David's lecture. And I can tell you it was deeply inspiring, and I hope that you will have as a profound feeling of this lecture that David will now start. Thank you very much, David.
Thank you, Carina, and I hope you can hear me, ladies and gentlemen. Let me know if you can't. First of all, let me start by thanking Carina and the whole of the Danish Semester Committee for inviting me to talk this evening. Also, I'd like to mention the JRC Ispra Cultural Association, ACE. If you haven't heard of us before, please do have a look at our website, because we organise all kinds of interesting cultural events, both here in the clubhouse, but also in Milan, many cultural and musical events in Milan. Let me thank in particular Candice for preparing the poster for this event. For Marcos, I think he's gone now for helping with the audio-visual, and for Valentin, who is here tonight, to film the event. That's the first time I think we've filmed something in one of these conferences. And let me thank you all, ladies and gentlemen, for sparing the time to come this evening. I'm very pleased also to see some of our colleagues from Amici della Storia with us tonight as well. So, Denmark has always punched above its weight in science. As Carina mentioned, in fact, 3 of history's greatest scientists are actually born and bred in Denmark. Tycho Brahe, who was the Renaissance naked eye astronomer who took measured the data about the planets, which was used then by Kepler to prove that Copernicus's theory that the planets rotate around the sun rather than the Earth was true. Then Hans Christian Ørsted, who, apart from discovering aluminium, was the first scientist to realise that an electric current generates a magnetic field, which is crucial for the operation of the electric motor. And as far as I know, Ørsted is the only leading scientist whose brother was a prime minister. Prime Minister of Denmark was his brother. And then the subject of this evening's presentation, probably the greatest of those 3, Niels Bohr. Now, in 1919, Einstein said of Bohr, who was 6 years younger than him, by now Einstein was already a world-famous professor, even at the age of 40, but he said of Bohr, his must be a first-rate mind, extremely critical and far-seeing, which never loses track of the grand design. And what I'd like to try and illustrate to you tonight is why history has proved, after 1919, that Einstein was exactly right. Now, in fact, Bohr revolutionized science by readdressing one of its oldest problems, one of its oldest questions: what is the universe made of? And in fact, this problem dates back to the ancient Greeks. And Democritus, something like nearly 2,500 years ago, came up with this most incredibly visionary statement. How he did it, I have no idea. Matter is made up of atoms in an empty space which attract and agglomerate together. And really, after that, on the subject of atoms as such, not much progress was made for over the next 2,000 years. until the time of the Industrial Revolution, when a scientist called John Dalton, working in Manchester in England, started to study how it was possible for various different compounds to be made from the same pair of elements, depending on the different proportions of the elements that were involved. And he developed something called the law of multiple proportions, which is written there, but I won't go into it just now in detail. But basically, he postulated from that law that atoms actually exist and came up with this atomic theory. Elements are made of extremely small particles called atoms. Dalton had no idea how small they were, but he knew they were very small. Atoms of a given element are identical in size, mass, and other properties, whereas atoms of different elements differ in size, mass, and other properties. Atoms cannot be subdivided, created, or destroyed. Atoms of different elements combine in simple whole number ratios to form chemical compounds. So, for example, carbon dioxide has one atom of carbon and two atoms of oxygen. And then in chemical reactions, atoms are combined, separated, or rearranged. And those 5 laws have basically underpinned chemistry ever since, and are still the foundations of all the everyday industrial chemistry going on around the world. Now we know that post-quantum mechanics, they're not all exactly true, but they're still pretty reliable for everyday activities. Dalton also drew up this list of elements that he knew about. You can see them there. He tried to work out, by looking at the different proportions, what he thought the atomic weights of the elements are. And he didn't get them all right because he made some wrong assumptions, and his equipment for measuring weight, particularly of gases, wasn't very advanced in those days. But he started on the idea of listing the elements. And then about 100 years later, by which time many new other elements had been discovered and experimental techniques had been radically improved, the Russian Dmitry Mendeleev started to work out how to classify the elements into groups. And he worked out that if you prepare a list of all the elements in order of atomic weight, but you put them down in columns, 8 columns, which you can see there how he's done it. Each column corresponds to elements of very similar chemical properties. So if you look at column number 7, for example, it has fluorine, chlorine, bromine, and iodine. Those are the so-called halogens, and they all have very similar chemical properties. Now, he didn't really understand why this was happening, but it was a crucial observation and helped in particular for identifying many further elements from then on. Interestingly enough, I can tell you a little story about Mendeleev. He was the first scientist to engage in science for policy because the Tsar of Russia gave him the job of standardizing vodka, because trade in Russia depended very much on making sure that vodka was all of roughly equivalent quality. And it was Mendeleev who worked out that all vodka on sale in Russia should have 40% alcohol. So if you've ever wondered why most spirits on sale around the world have 40% alcohol, then that's thanks to Mendeleev, who invented the periodic table. Then, just after that, in 1895, there was a complete revolution in science, which started, in fact, strangely enough, with 2 completely accidental discoveries. First of all, in 1895, Röntgen, working in Würzburg, discovered X-rays and their magical properties of passing through flesh, allowing doctors to make images of the bone structure of living people. So that was a massive step forward. But then the very next year, Henri Becquerel, working in Paris, again by accident, discovered that if you leave uranium in a completely darkened room, he'd accidentally left some photographic paper in the room. When he came back, he discovered this photographic paper had been exposed. So there was no light in the room, and it seemed as though this uranium was giving off something that originally they described them as Becquerel rays, because he discovered them. Even though there was no sort of energy source going into this uranium, it seemed to give out energy in the form of these Becquerel rays. Then in 1897, J.J. Thomson, Professor Thomson, working in Cambridge, discovered a particle much, much smaller than the hydrogen atom. Up until then, everybody had thought the hydrogen atom was the smallest possible particle in the universe. But then he discovered a negatively charged particle, less than 1,000 times smaller than a hydrogen atom, and he called that the electron. Marie Sklodowska-Curie, the only person, by the way, ever to win 2 Nobel Prizes in 2 different subjects, still to this day, and her husband Pierre did a lot of research into the Becquerel rays, coined the term radioactivity, discovered 2 new elements, polonium and radon. And then in 1900, Max Planck, working in Berlin, was studying the light emitted by hot bodies. Like, for example, you know that iron red, if it's very hot, it glows red, and then if it's even hotter still, it glows white. So he was looking at the spectrum of light given out from these bodies, and he worked out a mathematical formula which fitted perfectly the data, and it seemed as though this mathematical formula was implying that light, instead of being a sort of continuous waveform, was actually small packets of energy, individual small packets of energy. And then in 1905, of course, Einstein, famously working as a patent clerk in Bern in Switzerland, produced 4 papers, one of which was described as being on the photoelectric effect, discovered indeed that light is not a wave, or it's not only a wave, it's also a stream of tiny particles, massless particles with energy, which were then later called photons. And that then takes us on to Niels Bohr's mentor, Ernest Rutherford. He was a New Zealander who'd come to Cambridge, gone then to Montreal, then come back to Manchester. And he was also looking at these Becquerel rays, now radioactivity, and he described them, or worked out there were 3 different types: alpha rays, beta rays, and gamma rays, as he described them. And he tried firing the alpha rays at very, very thin gold foil. And he discovered that most of these alpha rays passed straight through with no interaction at all with the gold foil. But then every so often, one of them, or a little particle from one of them, seemed to bounce back, like a tennis ball bouncing off a brick wall, more or less straight back the way it came. And he concluded that atoms are basically empty. There is a cloud of these very light electrical negative electrons somewhere around the outside, but all the mass of the atom is concentrated at a small bit right in the middle, which he called the nucleus. And just to give you an idea about the size of this nucleus, if you imagine a hydrogen atom expanded to the size of the dome of St. Peter's in Rome, St. Peter's Basilica in Rome, then the nucleus would be about 4 millimeters across. So the rest of this great space, completely empty. And of course, that was a great surprise to people who'd imagined atoms were little blobs of something. And then that takes us on now to our today's hero, Niels Bohr. He was born in Copenhagen in October 1885. Here's a picture of his family. Niels is actually standing there behind his sister, big sister Jenny. His father was Christian Bohr, who was a very distinguished professor of physiology in the University of Copenhagen. His mother was Ellen Adler, who in fact was the daughter of a very wealthy Jewish banking family in Copenhagen. And his younger little brother there, Harold, who's a couple of years younger, is famous for two things. He actually became a distinguished mathematician in his own right, but he had a silver Olympic silver medal, because he played football for Denmark in the 1908 London Olympics. And Denmark was in the final. Fortunately, they lost because England won that final. But Harold Bohr came back with a silver medal from the Olympics. Now, Bohr went to Copenhagen University, started as an undergraduate in 1903, had a PhD in 1911 on electron theory in metals, so already quite an advanced subject for a PhD. And then he won a Carlsberg Foundation scholarship to go to Cambridge. He worked for a while in Cambridge, but then decided that it would be more interesting to go to Manchester and join Rutherford, who was working on the atom. And Bohr came up with a very interesting postulate. He said that probably the electrons in the atom orbit the nucleus in a little bit the same way as planets orbit the sun, but with one major difference. A planet, in principle, can orbit the sun at any different radius away if it has the right speed. But electrons can only orbit in a very definite number of fixed shells. This is the quantum aspect of his model. It corresponding to a specific set of fixed distances from the nucleus. And then if you put, say, hydrogen gas in a gas discharge tube with an electric current flowing through it, then sometimes one of the hydrogen atoms might absorb some energy from the electric current and jump up from the closest orbit to the nucleus to a higher orbit. So going from, say, n equals 1 to n equals 2 or n equals 3 or n equals 4. And then spontaneously and instantaneously, for no particular reason at all, suddenly decide to drop back down from whatever orbit it's in to a lower one. And as it does that, it emits a photon, a little energy packet of light of a very specific colour. And Bohr was able to predict exactly the colour spectrum of light emitted from a hydrogen gas discharge tube. And that fitted precisely with experimental data and gave his theory a lot of experimental support. And he went on then also to explain how the electrons of all of the elements were arranged in the different orbits around their respective nucleuses. So here's a picture, for example, of carbon. It has 2 electrons in its inner orbit and 4 in its outer orbit. And then it can form stable compounds, Bohr explained, by joining together with other atoms so that pairs of electrons, so here in fact is a picture of methane, where 4 hydrogen atoms combine with 1 carbon atom, and each hydrogen atom shares 1 electron by kind of forming a pair with one of the 4 electrons in carbon's outer shell. And that's stable because carbon has this feeling it's got 8 electrons round its outer shell, and that gives it this feeling of being a kind of complete shell and therefore highly stable. Now, with this analysis, Bohr basically explained Mendeleev's periodic table. He gave a kind of physical understanding to the table. And in a sense, he therefore explained entirely how chemistry actually works. And he was able to go on and extend the periodic table. This is a view, this is actually a modern periodic table, but based on Bohr's theories. And it shows for every different element exactly how all the different electrons in each element are arranged into shells, starting with hydrogen and going up to the very highest radioactive element at the very end of the table. And Bohr was able to predict from this table how you might find new elements that hadn't so far been identified, and in particular element number with 72 electrons, that's its atomic number is 72, hadn't been identified. And Bohr said that it's going to, looking at this table here, you can see I've marked it with a yellow marker, that's element number 72. He said it would have very similar chemical properties to the two above it, which is zirconium and titanium. And sure enough, he then set the geologists in Copenhagen and the mineralogy department to look in their collection for something similar to zirconium and titanium, and very quickly they came back with a new element that they discovered, and it was called hafnium. It was called hafnium. Hafnia being the Latin word for Copenhagen. So that new element that Bohr basically discovered was named after Copenhagen. Now, at this point, Bohr, who's still only a very young man, just 32 years of age, made a very important step, because he was able to influence policymakers and decision makers. And he persuaded the Danish government and the Carlsberg Foundation to provide the money for a new institute in Copenhagen, the Institute of Theoretical Physics. And as you'll see, that turned out to be a crucial and very important step for all of us. He was invited just after the end of the First World War to go to Berlin, where he met Max Planck and Albert Einstein. Already at that stage, Bohr and Einstein started an important discussion which went on for many years, because I explained how spontaneously these excited hydrogen atoms suddenly emitted a photon. Einstein didn't like that because he couldn't understand what caused the specific event of any one particular atom to emit this photon. And Bohr argues that nothing causes it. This is a feature of quantum mechanics. It just happens. It happens with a certain probability, but basically at random. Einstein didn't like that aspect of quantum theory at all, and it took many years before finally this sort of strange aspect of quantum physics, which is totally different to classical physics, was accepted. Now, in 1921, the Institute of Theoretical Physics opened in Copenhagen, and it very rapidly became the world-leading centre of modern theoretical physics. It was visited by all the top scientists, either for long or short periods, including many of the great young scientists who would go on to create the world of quantum mechanics. But I think very importantly, and this is a great tribute to Bohr, but also to Denmark, he was able to reunite European science following some of the difficulties that had arisen during the First World War between particularly, obviously, Germany and France and Britain. So that was a great step that Bohr, with his personality and this initiative of setting up the institute in Copenhagen, made an enormous impact on. In 1922, Bohr was awarded the Nobel Prize in Physics for his investigation of the structure of atoms and the radiation emitted from them. And I think it says a lot about Bohr that he was, in the same year, actually, Einstein was awarded the deferred 1921 Nobel Prize. In fact, for the photoelectric effect, not for relativity, you might be interested to hear. But Bohr was very happy, it's reported, that he hadn't got his Nobel Prize before Einstein. He thought that, you know, Einstein was the older and the more brilliant scientist, and it was very important in Bohr's mind that credit was given where credit was due. And I think that says a lot about him. And as you'll see, he turned out to be a brilliant collaborator across the field. Then, with the Nobel Prize now, Bohr's network expanded. He really became a kind of a high priest, the hub of a network, but very much revered by many, particularly of the younger scientists. But he created a network throughout Europe with collaborators in Zurich, Göttingen, Rome, Dirac in Cambridge, Paris, Moscow, Leiden, Berlin, and elsewhere. So Bohr was really sort of holding together a European network in quantum mechanics. And I think particularly important in that context was Heisenberg. Heisenberg actually came to Copenhagen as part of his PhD. As a very young man, just 21, he spent a year in Copenhagen. And then, when he finished his PhD, he came back to Copenhagen as a postdoc, and he was appointed as Bohr's assistant. And Heisenberg was a mathematical genius. In Germany, they called him der Wunderkind, and I think that's probably entirely appropriate. He quickly developed a very complex mathematical model, a matrix mechanics mathematical model, which described fully quantum mechanics and was able to go on beyond Bohr's theory, calculating how more complex atoms would behave. And the reason why 2025 is regarded by many as the centenary of quantum mechanics is because Heisenberg developed that mathematical theory in 1925, and right across the world, actually, during this year, there have been many conferences in universities and elsewhere celebrating the 100 years of quantum mechanics. Heisenberg went on then, while still at Copenhagen, to develop the famous Heisenberg uncertainty principle, which says, again, a strange feature of quantum mechanics, that you can't detect both the momentum and the position of an electron precisely at the same moment. And at the same time, Bohr announced the complementarity principle, which says that just as Einstein had discovered that light could be treated not only as a wave, but also as a stream of particles, Bohr said electrons can be considered not only as a stream of particles, but also as a wave. So he had exactly the kind of complementary principle there and in the opposite direction to Einstein. Then in 1927, Bohr came to Italy to the Como conference, which was actually organised by Mussolini to celebrate the 100 years of Alessandro Volta. It was a very important conference. Fermi was there, as indeed was Marconi. It's one of the only science conferences ever to be broadcasted on national radio, because Marconi was there to organise the broadcast. But this was where Bohr first announced the complementarity principle and started to gain momentum. And then just exactly 1 month later, in Brussels was held probably the most important scientific conference that's ever taken place. This was, in fact, the 5th Solvay conference in Brussels. Those of you who visit Brussels very often, or who've even lived in Brussels in the past, will recognise that building, which is still there. It's in Park Leopold. But at this conference, and some of you might be able to make out on the front row of the image there, Marie Curie, who's sort of second from the left on the front row. Also Einstein is there in the middle of the front row. Bohr himself is at the right-hand end of the second row. In that conference, there were 29 people. 17 of them would either already had or would go on to win a Nobel Prize. And it was at this conference that really quantum mechanics started to gain widespread acceptance amongst the leading scientists of the day. Now, this image is an image of 3 of Bohr's disciples. In fact, they're there with, this is Heisenberg, Dirac, and Schrödinger. Schrödinger is actually the one on the right-hand end of the 3 men, then Heisenberg in the middle, and Dirac, the tall one, in the middle. And they're actually there with Heisenberg's mother, Schrödinger's wife, and Dirac's mother. And the picture shows them arriving at Stockholm railway station in time for the Nobel Prize ceremony in 1933. These 3 of Bohr's disciples were awarded the Nobel Prize for Physics. In fact, it was Heisenberg's getting the 1932 prize, which was deferred, and the other 2 in 1933 for their work on quantum mechanics. And it's really the work of those 3 mathematicians, coordinated and inspired by Bohr, which created the modern quantum mechanics. Now, just in case you think that quantum mechanics is sort of some esoteric mathematical theory, I can tell you it's not. It's the fundamental driver of much of the economy that's been developed since the Second World War. In 1947, in Bell Labs, the Bell Telephone Company labs in America, the transistor was invented by these 3 gentlemen. It's based entirely on the physics invented in quantum mechanics. Here actually is a picture of a transistor radio in 1970. In 1970, I was 14, and that was exactly the time when everybody who was 14 wanted a transistor radio, and this is one of the ones that I was, I don't know whether I had exactly this one, but it was a wonderful achievement. If you had a transistor radio, you could go around listening to the radio wherever you wanted, instead of a huge, great machine at home. That transistor radio has 8 transistors in it. I don't know whether anyone would like to have a guess, but does anyone want to have a guess at how many transistors there are in an iPhone 17 Pro? It's 30 billion. 30 billion. So, and a thing roughly the same size as that transistor radio with 8 transistors in 1970, we now have 30 billion. There's something. You've all seen, you can invent this slide just as well as I can, the ongoing electronics and data digital revolution. We're now doing artificial intelligence, of course, and right now the tech giants are investing $1 trillion in infrastructure for artificial intelligence. Quantum computing probably coming relatively soon, and that could change the whole world of computing. The revolution in quantum mechanics is still going on. In fact, the 2025 Physics Nobel Prize is also awarded to 3 scientists working on quantum mechanics. from the University of California. There they are. One is in fact French, one British, and the other American. Now, let's go back to Bohr, because in 1932, a man called James Chadwick, working with Rutherford in Cambridge, discovered a neutral particle, electrically neutral particle, with the same mass as that of a hydrogen atom. And Bohr postulated that the nucleus is made up of positively charged protons, neutral neutrons, all held together somehow inside the nucleus. And Bohr made a kind of a postulate that it might be something similar to a drop of liquid held together by the forces of surface tension. And based on this postulate, he was able to work out with a man called James Wheeler, an American who was visiting Copenhagen at the time, a mathematical theory to describe how he thought the nucleus was held together, called the liquid drop model. Now, in the meantime, Enrico Fermi, working in Rome, had discovered that if you take uranium and bombard it with these neutrons, you can actually create new heavy elements, including, for example, plutonium. Uranium can absorb neutrons and create new elements. But then, in 1938, Otto Hahn in Berlin discovered, or he observed really, something very strange, which is that sometimes when a neutron hits a uranium element, it more or less split the nucleus in half. And Lisa Meitner and Otto Frisch, who were in fact German but had moved to Stockholm during the 30s, used Bohr's theory to try and explain how this process, splitting a nucleus, or fission, took place. And what they worked out was that it could only take place if the nucleus was a particular isotope, a particular type of uranium with uranium-235. And when a neutron comes in, first of all, it's absorbed by the nucleus, making something uranium-236. But it sets up a kind of oscillation inside the nucleus, which causes a kind of necking. And a liquid drop can neck sometimes and split into two smaller drops. And indeed, that's exactly what happened. And the two elements produced, two much smaller elements, krypton and barium, and a number of more neutrons were emitted from this process, two or sometimes even more. And therefore there was a possibility of a chain reaction, because these new neutrons might go and find more nuclei to react with. But in particular, this process would generate an enormous amount of energy. Every time one of these fissions happened, something 200 million electron volts would be emitted. Now, I'm not sure if everybody here knows how much is a million electron volts, but I can give you an idea, because if you take 1 gram of uranium U-235, if you are able to make the whole of it fission, so you completely split apart every nucleus in it, then you get as much energy out as you would by burning 4 tons or 4 million grams of coal. So you can see that the energy production from this process is potentially enormous in comparison with any of the energy producing processes that were in use at that time. Now, after that, just after the discovery of fission, war broke out in Europe. And in 1940, the Nazis invaded Denmark and occupied it. And then in 1941, Heisenberg came from Germany to visit Bohr. Now, Heisenberg was not a member of the Nazi Party. In fact, he was actually regarded with suspicion by the SS because he was considered to be too friendly to Jews. But nonetheless, he was the most brilliant physicist in Germany, and he was a loyal German, and he was appointed by Hitler to lead the German, or they should really say the Nazi, atom bomb project. And it's been debated long and hard exactly what happened in this meeting between Heisenberg and Bohr. And there were contradictory opinions coming from the two people who were present. Did Heisenberg come to ask Bohr's advice on maybe he just came to visit his old friend because they'd been working together for many years. Did he come to ask his advice that could be useful? Did he even come to try and recruit Bohr to join the Nazi program? Or did he come to warn Bohr what was going on in Berlin? We will never know the answer to that. I should say, of course, Heisenberg went on to be a very important figure in Germany. He was the leader of the Max Planck Institute after the war, and was very much involved in the first nuclear power in Karlsruhe. The nuclear power plants first built in Karlsruhe were under Heisenberg. Now, in 1943, the Nazi race laws were going to be implemented also in Denmark, and Bohr managed to escape to Sweden with the agreement of the King of Sweden. And he then, from Sweden, he was flown by air in a military aircraft to Britain, and eventually went to the United States. In fact, 7,000 Danish Jews escaped to Sweden from Denmark, and it's been suggested that, in fact, Bohr was instrumental with the King of Sweden to arrange the escape and the accommodation of these Jews escaping from Denmark. I don't know whether that's really fully documented historical proof, but I've heard it suggested in various books that Bohr was strongly influential in that activity. Now then, Bohr became a kind of consultant on the Manhattan Project. In fact, he was known while he was there, not as Niels Bohr, but as Nicholas Baker, because it was considered highly confidential that Bohr was there in America at the time. This picture shows Bohr with Oppenheimer next to him. The other one at the front is Enrico Fermi, who of course was working on the first nuclear reactors at the time. And behind them is Richard Feynman. And Feynman actually became a great physicist. He was the greatest physicist really since that generation. He developed quantum electrodynamics, the most accurate theory ever produced in physics. According to Feynman, it was so accurate and agreed so closely with experiment that it was equivalent of measuring the distance between New York and Los Angeles to the width of a human hair. So it was the equivalent accuracy in terms of precision. But also, it's interesting, if anyone here thinks they don't quite understand quantum mechanics, well, I can tell you you're in very good company, because Feynman famously said that nobody really understands quantum mechanics. It's just, for us humans, it's just impossible to understand it in the same way as we understand classical physics. And I have to say that having read various books that are aimed at the layman on quantum mechanics, which you think, oh, well, if I read that, I might understand it. Well, at the end, you don't understand quantum mechanics. All that happens is you finish understanding what you don't understand about it. And I think that Feynman was dead right. Don't try and understand it. For physicists, it's just really a mathematical tool that you use to make very accurate and very reliable predictions about the subatomic world, but you can't really understand it in the same way as you can classical physics. Now, while he was there on the Manhattan Project, Oppenheimer suggested that Bohr had in fact made a crucial contribution because the bomb that uses plutonium, which in fact was the one used on Nagasaki and which subsequently, but basically all atomic bombs ever designed since use, needed some. It's very difficult to make a bomb that will start with plutonium. You need to kick-start somehow the fission chain reaction. And it was Bohr, apparently, who came up with the clever solution to that. I have to say, I don't think it's public knowledge exactly how it works even to this day, but it's something that Bohr has been credited with. Bohr then went on to do his best on strengthening international nuclear collaboration. To start with, while the war was still going on, he strongly believed that when the war was over, it would be important to have maximum collaboration between the West and Russia. And he tried to convince Churchill and Roosevelt to share what was going on Manhattan with Stalin. And he actually met both of them individually. He was able to get a meeting with Churchill and then with Roosevelt. I have to say that after the meeting, Churchill said that he and Bohr didn't speak the same language. And I don't think that was because of Danish and English. I think that was probably because scientists and politicians don't always speak the same language. I think he got on a bit better with Roosevelt, but he wasn't able to convince them to share the progress with Stalin. Whether the world would have been different ever since if Bohr had been successful with that, who knows? Your guess is as good as mine. But where he was very successful then was in 1950 when he convinced the newly formed United Nations organization to encourage international cooperation in the peaceful use of nuclear energy. And as a result, very distinct result of Bohr's personal initiative, the IAEA, the International Atomic Energy Agency, was born in 1957, the same year that the Euratom Treaty was born, and which eventually, a few years, well, just 3 or 4 years later, led to the development of the JRC. In 1957, Bohr received the first Atoms for Peace Prize because of his efforts in establishing the IAEA. And it's basically, if international treaties that you've heard of many times, particularly between the Russians and the Americans, but also right around the world in terms of things like the Nuclear Proliferation Treaty, if they work, it's because the IAEA have the technical competence to monitor these things and check that they're actually being adhered to in the various states involved. Now, nuclear energy has gone on to become an important activity particularly, of course, for electricity production. And you can see a graph here of all the different sources of energy produced in the world today, going back over time. Nuclear went up very significantly in the 70s and 80s. Then it started to level off in the 90s. And that's, of course, following the accidents, 3 Mile Island and Chernobyl. You can see that what's worrying about this graph is that coal and gas are still increasing. I was a bit surprised to see that coal is still increasing. Gas, of course, still very important for energy production. But if indeed we're going to stop the use of fossil fuels, how are we going to do it? Wind and solar have increased quite a bit there, but are they going to really be able to make up for everything that's been lost from coal and gas, particularly as energy consumption, electricity consumption looks as though it's going to go up? I don't know. I mean, experts say we need nuclear as well. Your guess is as good as mine. I know people have different opinions about that, but certainly it seems as though something is going to have to change, particularly with all these data centers now coming online. We're going to need a lot more electricity for our cars, but for, the AI requirements are going to be enormous. Of course, nuclear physics is also important in various medical treatments. And it was actually Marie Curie who first discovered that radioactivity was effective for treatment of certain types of cancer. And of course, that's gone on to enormous success since. Now, after the war, the centre of gravity of theoretical physics started to move across the Atlantic. We already talked about Richard Feynman, but America started to become the leading country in the world. But Bohr was very keen to make sure that Europe stayed at the forefront. And again, it was Bohr's initiative to set up CERN, the European Organisation for Nuclear Research. I wish it was called the European Organisation for Subatomic Research, really, because, of course, this is not to do with nuclear energy, CERN. It's to do with the fundamental physics of the nucleus and the subatomic particles. It's been a great success. And in fact, the CERN theory group was initially hosted in Copenhagen. And I think it's thanks to Bohr that, Europe's still a leading player in high energy physics. He also managed to keep Scandinavia at the forefront. He was able to found and become the first chairman of the Nordic Institute for Theoretical Physics. That again started in Copenhagen, but it's now based in Stockholm. And Bohr helped also the setting up of the Riso National Laboratory of the Danish Atomic Energy Commission. Actually, that's now part of Technical University of Denmark in Copenhagen, and it's focused mainly on non-nuclear sustainable energy. But when I first joined the JRC, the chairman of the board of governors of the JRC was the director of Riso. So Riso has had quite an important influence over the years on JRC development. Bohr has been given many awards from around the world. I think probably the most important of all was the Danish Order of the Elephant. And Danes here will tell you that that is the highest possible honour in Denmark. It's normally reserved only for royalty, and it's not given out very often. So this was a real achievement for Bohr. But also, just shortly after he died in 1965, the Copenhagen Theoretical Physics Institute was formally renamed the Niels Bohr Institute. And then in 1997, the newly discovered element with atomic number 107 was named bohrium. So Bohr joined the very few distinguished scientists who actually have an element named after them, including, of course, Einstein, Rutherford, Curie, and the like. Now, as I said at the beginning, Einstein had a very high opinion of Bohr. In fact, he said two things about Bohr. First of all, he said that the Bohr atom is the highest form of musicality in the sphere of thought. And coming from Einstein, that's a pretty important statement. He also said, as I told you at the beginning, his must be a first-rate mind, extremely critical and far-seeing, which never loses track of the grand design. And I think Einstein was right, essentially for the following reasons. Einstein had his own brilliant idea in 1913, and indeed another one in 1933. But that was only really the start. He became the hub, the father figure of a group of European scientists who, together by 1927, had completely transformed our understanding of what the world is made of. And by doing that, he essentially paved the way for the digital revolution and the peaceful use of nuclear energy, both of which are still in development today and which are very important for all of us. And I think really Bohr did that because he was a natural leader and collaborator. This was his, I mean, there are many brilliant, well, there aren't many, but there are quite a few brilliant scientists. For example, Einstein himself, probably even more brilliant than Bohr on the science per se. But few people have combined that kind of brilliance with the human skills necessary to lead and get people to collaborate together in such a constructive way. And I think that that's really what makes Bohr unique and, in my personal opinion, the most important scientist of the 20th century. He also, of course, believed in very strong international collaboration, and I think that's crucial. He realised that competition wasn't going to work in fundamental science. The best way forward was international collaboration, and he did a lot to promote that. Now, let me just finish by telling you a little story about Bohr. One day, a visitor came to Copenhagen, and Bohr invited him to come for dinner at his home. And when the visitor arrived at Bohr's house, he was surprised to notice a horseshoe nailed above the door, the entrance door of the house. And the visitor said to Bohr, well, surely you're a great scientist, a great man of science. You can't possibly believe in the old story that horseshoes bring good luck, can you? That can't be possible. And Bohr said, well, no, of course I don't believe it, but I'm told that the horseshoes work whether you believe in them or not. So, ladies and gentlemen, thank you for your attention.